Welcome to my talk. I'm Hakan and here to talk about composing view models. In this talk, we'll be introducing our new UI architecture, which is called microfeatures. Microfeatures depends on the idea of breaking view models into smaller self-contained UI models. And I'm working as an Android engineer in Delivery Hero, and our company is present in 70 countries, more than 70 countries, and its main mission is to deliver anything straight to customers' doors. So our team in Delivery Hero is responsible for developing this rider application for all these brands, and all the applications are different branding of the same rider application. And main functions of our rider application is to allow riders determine their working hours, start working, accepting their orders, and also performing some delivery tasks like pickup, drop-off, etc. Recently, there has been a major change in our app scaffolding initiated by our designers and product teams. And because of this change, we needed to invalidate our current UI architecture. And in this talk, we'll be talking about this change, this shift. And let's look at this major change from a design perspective together. So this is our old design, and here we have dedicated tabs for each main functionality of our app. For example, status tab is for determining our riders' working hours, starting to work. Delivery tab is for delivery tasks like pickup and drop-off, as I mentioned. And all these functions were totally isolated from each other in different tabs, and they were owned by different teams. After running several user studies, design workshops, and competitor analysis, our product and design teams decided to move to a new UI design to provide a better user experience for our riders. And this is our new design. And as you see, it doesn't have button navigation, and we don't have any tabs. So home screen is the only screen, and it provides access to all content and features. And this is actually this change targeting UI only, and our source of truth for the domain is not changing, but we are changing how we present this data to our riders in a context-aware manner. Since this is just one screen and several teams need to work on the same screen, this is a huge change in the app scaffolding of the app, and also a big change from the ownership of features perspective. So this change actually comes with a very critical question. How can we continue developing our rider application with 8 teams while everyone wants to show their content on a single shared screen? So in this talk, we are going to propose an architecture that will help to overcome this challenge. So before diving into this solution, let's identify the architectural requirements needed to support this design shift. Depending on the new design requirements, our architecture should enable showing dynamic contextual content on a single screen. This is our first requirement. And the other one is enable showing UI components that are backed by different data sources. So in the same screen, you will have UI components, and they will be able to get their data from different data sources. So it should foster portability by enabling composition of UIs in any host. Now we have this host keyword, so we are not talking about screens anymore, but host will be coming to that part more in detail soon. And also this portability, we will have UI components, and then we'll be able to move them around in different hosts with minimal integration effort. And while doing all this, we should keep loose coupling between features, squads, and domains. This is also really critical because we are 8 teams, and we should still deliver in isolation while working on the same screen in a collaborative manner. So let's do a quick architecture review. Actually, we have a question here. So this question is, does our current architecture support these requirements? Let's run a quick architecture review to answer this question. So, before asking the first question of the architecture review, let's go a bit back in the history of Android development. All the story started with activities, and we were using them to write all our UI logic, and in most of the cases, our business logic was also being implemented in those activities. And then these fragments have arrived. We had new classes to offload our code from activities to fragments. So activities were a bit fat, and then we moved some content from these activities to some other fragments. After that, MVX patterns have become popular, and Google came up with an opinionated solution called Jetpack ViewModel. And these ViewModels are equipped with some superhero powers like configuration chain survival, ViewModel scope, safe state handle, etc. It's growing every day. So, and we found more space to write some code. Of course, this story didn't finish here. New features arrived from product teams, fragments got bigger, ViewModels got bigger. Adding a new feature became more complex than before. Then we started to receive some signals from our fragments and ViewModels. So, and then our teams started to work on these, and these tech debts actually were accumulating, and our teams started to work on these tech debts, right? Actually, it didn't go in that way, and we didn't start working on these tech debts, and we ended up with fat fragments and fat ViewModels, which are hard to refactor and maintain, and they were ready to explode. I think this story should be familiar maybe for some of us or most of us here in this room. It has been a very similar experience for us in our Rider app as well. And after this brief, let's say, recap of evolution of ViewModels or fat ViewModels, let's answer our first question. Is it possible to reuse UI logic from the existing ViewModels? They are too complex, and as you see here, and I think the clear answer is no. And the next question is, here is a screenshot from our old UI, and it has several UI components for different rider status scenarios. And our next question is, can we reuse these components in our new design? So, these UI components are tightly coupled with host fragments. They have all these recycler view complexity like view holders, delegates, other stuff. There is a huge one UI state mapper for the whole screen, and it's really complex. And they are not written in Compose. Of course, this is not a hard requirement, but nowadays it's better, maybe, you have things in Compose. So I think the obvious answer for this question is also no. So we cannot reuse them. So the next question is, can we reuse our data domain layers as they are? Thanks to our observable repositories and domain use cases, I think we can answer this question as yes, and we were able to use actually 80–90% of our data domain layer as they are, because the main shift was on the UI. So, after reviewing our architecture, we decided that we need a paradigm shift in our feature development process. So this change is, rather than creating an isolated screen and then implementing UI components specific to that screen, we are going to create self-contained, host-agnostic, plug-and-play UI components and then compose our UIs using these components. This was actually our paradigm shift, and we called this self-agnostic, self-contained, host-agnostic UI component as microfeatures. So, before diving into details of microfeatures, let's see some example microfeatures here. These are all from our application. I think seeing them as they are implemented will make it easy to understand the concept of microfeatures. All the components here are self-contained microfeatures which can live in any host in the home screen with minimal integration effort. So they can populate their own content, and they just need some minimal support from their host, as I mentioned So, after seeing some examples, let's explore the micro features in detail. So, we have actually a micro feature consists of a UI model and a composable. They are self-contained. They implement their own unidirectional flow. I will pass here a bit fast and come back later. They provide APIs, factory methods to create UI model and composable. They are host agnostic and needs a host to start functioning. They foster composition of UI models and composables. Here, actually, there are some keywords to highlight. These are UI model, unidirectional data flow, factory methods, provider APIs, host, and composition. So here, there is another question, actually. Before diving into details of these keywords, maybe you are wondering something, I'm not sure. We saw this UI model keyword in the first slide. Now it's the second time we are mentioning UI model. So what's a UI model and how is it different from a Jetpack ViewModel? So let's first try to answer this question. So this ViewModel keyword is already reserved by Jetpack ViewModel library. So when we say ViewModel, nowadays everyone understands this Jetpack ViewModel as Android developers. That's why we need to come up with another name for our ViewModels, and we called them UI models. Actually, ViewModels and UI models have a lot in common, but they also have some significant differences. Let's compare them. They populate and publish state to do UI. They both do that. They react to events from UI. They persist data through configuration changes. This is built-in feature of Jetpack ViewModels, but here is the idea. If you host your UI model in a view model, then your UI model will also persist data through configuration changes. We'll come to that later. And as you know, Jetpack ViewModel is Android only, and it's not platform independent, but you can write your UI models in a platform independent way. Jetpack ViewModels have this built-in coroutine scope access, and if your ViewModel has coroutine scope access, and if you are hosted by a ViewModel, then you can also have coroutine scope access. So easier test setup, as you know, there are some, I don't know, it's not that complicated in the end, but you need to, if you want to write some tests in your ViewModel with coroutines and other stuff, you need some setup. But for UI models, you don't need that stuff as well. So after comparing a view model and a UI model, maybe someone can ask, are we getting rid of view models? The answer is partially yes, partially no. So we want to use these super powers of view models while keeping our UI models platform independent. These maybe superpowers are ViewModel scope, configuration change survival, and safe state handle. But how can we achieve this actually? Let's see. Here is the idea. What about creating a parent-child relationship between a ViewModel and UI models so that ViewModel can pass these superpowers to its children? For example, in this scenario, we have 3 children UI models, and they are hosted by a parent Jetpack ViewModel. In this case, if ViewModel survive configuration changes, then UI model will also survive. UI models will also survive. These UI models are designed to be self-contained, and they are portable. They require only minimum integration effort from their parent. Before switching to that part, actually, this Jetpack ViewModel has this ViewModel scope, and also we have safe state handle. So we can directly pass our coroutine scope to our UI models through factories. And we can also create a very simple abstraction of key value pairs and then send them to UI models if they need, like safe state repositories. And of course, this is not needed for all UI models. And through factories, we can just provide as the host ViewModel what our UI models need. So actually here, these UI models are designed to be self-contained and portable, as I said, they require only minimum integration support from their parent. By using these UI models, we can compose bigger view models, and we can call this process as composing view models. Actually, the idea started here, and this is the title of the talk as well. Now we'll see more details about this one. So actually, we've seen the difference between a view model and a UI model, and we defined what a UI model is. And in one of the previous slides, there was also these keywords. One of them was unidirectional data flow. So how can we fit our UI model into this UDF? So here, there's a, I don't know, this is a very common UDF flow, and it should be familiar to everyone, I think, here. So here is the traditional UDF, and it's tailored for a micro feature. But when you look into this, you will see that it's really same what we are seeing for ViewModels or any other pattern. So the only thing that worth mentioning here is that this UDF here is like a micro level UDF, which is scoped to UI component rather than the whole screen. So in a single screen, you can consider that we are going to have as many UDFs, unidirectional data flows, as the number of micro features in that screen. This is a bit controversial to UDF, where you keep all screen state in a single state holder, generally. But now we are shifting our perspective. We are not building isolated screens anymore, but we are building self-contained components that have their own UDF flows. And using these self-contained components, we are composing UIs for any host. This is actually the change we are going through. Soon, actually, we'll be exploring a micro feature implementation in detail. Before that, let's explore the blueprint of a micro feature. So here we have a class diagram. It's spanning two modules, let's say Gradle modules here. And these modules are API and implementation modules. And as you know, this is a very common pattern to split API and implementation for features. So micro feature architecture also follows the same. And main components of this architecture are UI model and composable. As an implementation of UDF, UI model actually exposes its observable state, and also we use these one-time consumable actions while receiving events from the UI. So composable here is also receiving UI model and observing the state and actions. And when an event happens on the UI, it calls the relevant event handler from the UI model, so it completes this unidirectional data flow. But when it comes to a host and it wants to show this component on the UI, then it needs to use these factories. As the name suggests, UI model factory interface, this UI model factory is used for creating UI model, and composable factory is used for creating composable function references. Actually, here it's really critical. We are here returning a composable function reference so that you can invoke this function in the host and render the UI. So it's the function, it's being returned, and you need to invoke to render it in the host. The implementations of these features, as you see, even the composable implementation, everything else is being done in the implementation module. We just have interfaces in the API module. After seeing this abstract definition of micro feature, let's explore a micro feature implementation to make it more concrete. The name of our micro feature is foo. Foo is a feature that has a title, description, and a call to action button that goes to bar. Let's start with creating our UI model interface in API module following the blueprint. So foo UI model has an observable UI state. It's exposed through state flow, and we have this special construct action handler for one-time consumable actions. This is opinionated implementation, nothing to be done nothing to be, it's not related to microfuture architecture or something else. And here we have this on go to bar clicked event. And we also have our factory, and it explicitly says that if you want to create my instance, then you need to provide a coroutine scope. Yes. Let's briefly check our state and action data classes, which we've already seen in the interface part. So we have unavailable state, we have loading state, we have available state, and when it's available, we show this UI. And we also have some actions. It's like now we are defining our UDF components. We have our action, which are go to bar, and in error cases, we also show errors. These are one-time consumable actions. We have still this distinction, which is a bit controversial nowadays, which is recommended to have one state and then do it through that one, but we are still using these one-time consumable actions in our UDF flow. So here is the implementation. Now we are in the implementation module. UI model receives these dependencies to populate its content, and the implementation of the UI model factory is done through Dagger. Of course, you can just write this factory by your hand manually, but here we are getting the help of Dagger. And we have here 3 dots. Let's get into that one. And when our UI model is initialized, we just use a use case and then populate our content, populate our state, and push it to our UI observers. So in the same manner, we have this on go to bar clicked, and when we receive it, we just send action back to our composable so it can take the necessary actions following the UDF pattern. So we are done with the UI model implementation part. We defined it. Now we need to focus on the view part that will be consuming this UI model. We also have an interface. I think this part is more interesting. We also have an interface for our composable factory, which is called full composable factory. And as expected, it just returns a composable, which we named as full composable. Actually, what we are returning here is a higher order function. And this function has a signature as any other function, and it's defined by a type alias, so it's easy to maintain, because it's quite common in composables that you can have, I don't know, 7, 8 parameters, even more. So it's better we use here type alias, and then we don't need to put this signature in several places. And if you want to add 1 parameter, you just add here, and then in the implementation. This saves a lot of boilerplate code. And I just want to mention it again. Here, we are just returning a function reference that will be called on the host via invocation. After it's invoked, it will be rendered in the host. Let's implement our composable factory for foo. This implementation will also be done in the implementation module. So we are not leaking our composable implementation. Just to mention it again, it's a lambda function. We are not calling the composable, but putting it inside the lambda function that will be called on the host side. This is one of the critical aspects of our architecture. This allows us to keep composable implementations in the implementation modules while allowing hosts to access them through factories from API modules. So our composable implementations are encapsulated in implementation module. Let's dive one more level down and see our composable implementation. I think these are really straightforward. I want to go into details. This is just a simple composable implementation. Here we have our special construct, again, to handle actions. We can also skip that part. And this is how we render our UI. Since we received our UI model here, depending on the state that we have now, in unavailable state, we render nothing. In loading state, we can show something else, but we skipped for the sake of time. In available state, we show the full content, and full content is this. This is like 2 text and 1 button there, and that's it. Now we have our UI model composable, and provider APIs. All of these together, we call it a microfeature. So now it is ready to be consumed. But how can we display this microfeature? This is the question that we need to answer now. So let's go to next slide. So microfeatures, we first need to define hosts to use a microfeature and display them. Microfeatures cannot start functioning without hosts. So app scaffold is composed of multiple hosts. Each host uses microfeature factory APIs to populate its content. Hosts as containers can also define some rules to lay out their microfeatures. So it's a host decision about this. So for example, if this bottom sheet host, here I want to define some host before proceeding. Here, for example, we have home screen, and we have map host, we have floating layer host, which lives on top of map, but it's a separate layer. And we also have this bottom sheet host, and when you click on this island, then it opens this dashboard host. So we have 4 hosts in our home screen. But if you have your UI component, you can, for example, move it from bottom sheet to dashboard, depending on your context. So these microfeatures are loosely coupled with their hosts, so you can move them around. So for example, if this bottom sheet host wants to show our full UI component, then it needs to use factory APIs to create the UI model and composable and bind them so that they can start functioning. Now let's explore how a host can use these factory APIs and display a microfeature. Let's start from the root host, which is the home screen. So we talk about this map, bottom sheet, and other hosts, but there is also a root host. Let's call it home screen, the home root. So here we have, from ViewModel perspective, the root host is represented by this home ViewModel. And as you see, our hosts also have these factories as normal microfeatures, so we can create their UI models as well. So we have bottom sheet UI model, and we can create it through using its factory. We have a very similar implementations for map UI model, floating layer UI model. I didn't put dashboard here, but it's very similar. So actually, what we are doing here is that we are composing our home screen using these host UI models. Let's go one level down in the hierarchy and see what's inside bottom sheet UI model implementation. So here it seems that bottom sheet wants to show 3 UI components as a content. These UI components are implemented using the microfeature architecture. We've already seen how we implemented foo. Bar and buzz actually follow the same blueprint, so they are exactly the same method. And as you see, it's exactly the same method how we composed our hosts in the parent. Now we are composing our content in the bottom sheet, exactly in a similar way. I think it will be easier to see it on a diagram. So here we have foo, bar, and buzz microfeature UI models. We are using them to compose our bottom sheet UI model. And then we have bottom sheet UI model, map UI model, and floating layer UI model, and we are using them to compose our home view model. This is composing UI models part, and the view part is missing. So how can we integrate our composables into this tree? This is the next, I think, question that we need to answer. Actually, this is host. Bottom sheet content is the host for the bottom sheet. And it receives all factories for microfeature composables and also some functions that are needed to be provided by the host, like showing a snack bar like this. So here we are statically providing this one, but you can also do it with different configurations and dynamically get your factories and then populate them. This is just to make it simple. I put these factories here so we can understand it easily without any complexity. So if we go to more details here, how are we using our factories to create our composables? Here I'm using full composable factory to create full composable reference that will be invoked soon. And we are also using remember, so in every composition, we don't need to create them again and again. So here, we already have our UI models, right? Because it's already in the parent. We are receiving bottom sheet UI model. I can access the children UI models there. I have my composable function references, so now I can invoke them using UI models. So here, what we here we are actually binding our UI models with composables. And actually that's it. We bound our UI models and composables in the host, and they started functioning. So we are seeing something on the screen. Let's revisit our composition tree again. So now our bottom sheet content host is bound to bottom sheet UI model, and our full composable is bound to full UI model. Similar things for bar and buzz. And we also have the root home view model, right? So it's bound to home activity. So this is the whole picture of our composition. We only have this one Jetpack view model in this hierarchy, which is bound to home activity, home view model. All others are platform independent, we can say, UI models if we write in them in that way. This is the whole picture of the composition tree. So microfeature architecture is defined. An example implementation is shown. Maybe now we can talk about which use cases microfeature architecture should be a good solution, and for which use cases it might not be the best. So first, it's important to mention that microfeature architecture is not a UI framework, or it's not a library. So it's an architecture definition that promotes composition of self-contained UI components. So it can have several implementations. We are just showing one opinionated implementation of this definition. So microfeatures are good for highly dynamic apps with shared hosts. Our application is one of these. And maybe they could be an overkill for small apps with static layout. And they are designed keeping host independence and portability in mind. But it could be a bit over-engineering if there is no need for host independence and portability. I think this is very critical. It enables working with several teams on a single screen in collaboration. But it might not be the best, for example, for small teams with static layout apps. The microfeature architecture, of course, is not a silver bullet in the end. While using it, there are several pitfalls similar to any other UI architecture. I just want to go over some of these pitfalls here. So a microfeature should be a logical group, and it should mean something from business domain perspective. So it's not a good practice to oversplit the features into several microfeatures if they are not meaning anything by themselves. Similarly, it's better we keep our UI model hierarchies shallow, so we prevent having unmaintainable hierarchies. Also, another critical point is that we should always keep host independence in mind. We shouldn't require that much of things from our root, and so that our macrofeatures should require as less as possible from their hosts, and they can move around the other hosts in an easier manner. Now we have seen the concept of microfeature architecture and also an example implementation. Let's have a look at some aspects of this architecture in a broader level, so that we can see what this microfeature architecture is enabling for us now and what it can enable for us in the future. So we actually mentioned this plug and play and portability, I think, in many slides before. So the first aspect is portability. Let's say we have a scenario where we are showing these components in our home screen. Then our context is changed. And this context change triggered some UI changes in the screen. So another host become accessible. Maybe you remember this dashboard from the host slide. And this host is for showing the components which have secondary priority, while our bottom sheet is for showing the primary content, the highest priority items. So here, what's happening is that when context change, we are actually, this bar and buzz, we are considering them as they are not important anymore. So we are moving them to our dashboard, and then new two micro features are coming, which are X and Y, and we are just integrating them in the bottom sheet in a dynamic manner. So this slide actually clearly shows that how flexible is this architecture in terms of showing dynamic content. So we are moving these micro features from somewhere else to another place, and generally we are not caring that much about the root, the host, because our micro features are self-contained and host independent. So another aspect is multi-platform. Since we have a clear actually distinction between Jetpack view model and UI models, this implementation of micro feature makes it easy to move UI logic to Kotlin multi-platform. So here, for example, the root hosts can be platform specific. We can use Jetpack view model in Android, for example, but all UI models can be implemented using pure Kotlin without depending on any Android library. So this means, I think maybe 90% of your, even more, your UI model logic, view model logic can go to Kotlin multi-platform, like this. And this is also very, I don't know, nowadays, very hot topic, and there are several implementations of it. In our application, we are using server-driven UI in some parts of our rider application, but our application is not fully implemented with server-driven UI. Actually, while designing our micro-feature architecture, we always kept server-driven UI compatibility in mind, so that if we want to switch to this solution in the future, we didn't want to be the blocker for that. So how can we configure actually our micro features with a remote UI configuration that is received depending on user's context? So here's a scenario again. Our context changed. We received a remote UI configuration, and we stored it in an observable repository. And there are two observers, even maybe more. Here we have our host. This remote configuration has two parts. One of them is a layout configuration for micro features, and the other part is component data for micro features itself. So here, our host is observing this remote layout configuration part. We have our micro features, and they are taking the part of component configuration, and our host, using this remote layout configuration, doing this layouting between micro features. So this is just showing a structure. Of course, this is not implemented, but if you have well-defined components, what we are here saying is that it's easy to move to a server-driven UI after having these self-contained micro features. Actually, yeah, I think it's on time. To conclude, let's talk about what are the next steps. So maybe you also observed this. There is some boilerplate complexity with factory APIs. To have a better developer experience, we are planning to provide tools and auto-generate some stuff for our developers. And another idea is to share a KMM microfeature between Android and iOS and explore the boundaries of this architecture in multi-platform environment. And also, it's not a short-term goal, but we are also planning to experiment server-driven UI with microfeatures. So that's it. Thank you for listening.